The Air Staff Target number 1142 was circulated within the Air Ministry in September 1954, and it carried with it an admission that few in Whitehall were yet prepared to state plainly. The free-fall atomic bomb, the weapon around which the entire V-force had been conceived, was already obsolescent. Soviet surface-to-air missile development, observed through signals intelligence gathered at Cheadle and through the careful reading of TASS announcements at the Joint Intelligence Bureau, suggested that by the early 1960s no subsonic bomber would survive a run over Moscow at any altitude. The conclusion, set down in a paper drafted under the supervision of Air Marshal Sir Geoffrey Tuttle, was that the bomb itself must learn to fly the final 100 miles. The requirement that emerged, formalized as Operational Requirement 1132 in November of that year, asked for a powered standoff weapon capable of carrying a megaton warhead to a target 100 nautical miles from the launching aircraft, with a circular error probable of less than 1 nautical mile. The figures look modest now. In the context of British industry in 1954, with the de Havilland Comet still grounded after the Elba and Stromboli disasters, and the Bristol Olympus engine yet to reach its production form, they were close to fantastical. Nothing in the British inventory could even approach a Mach 2 cruise. Nothing in service used inertial guidance of any sort. The Royal Aircraft Establishment at Farnborough had only just begun the high-speed wind tunnel programme at Bedford that would make such speeds tractable in design terms. The Cabinet Defence Committee discussed the matter on the 23rd of February 1955 in a meeting chaired by Sir Anthony Eden, then still Foreign Secretary but soon to take the premiership from Churchill. The minutes, declassified and held at the National Archives at Kew under reference CAB 128/28, record Duncan Sandys arguing that the cost, then estimated at £4 million for development, was a fraction of the price of maintaining a credible bomber force without it. Sandys was, of course, mistaken about the cost by an order of magnitude, but the argument carried the day. Treasury approval was granted in May, with the qualification that the project should be reviewed annually. What the Air Ministry did not entirely concede in those early papers was the sheer novelty of what it was asking for. The Americans were pursuing their own standoff weapon, the GAM-77 Hound Dog, but they had the advantage of a vast missile industry already mature from the Snark and Matador programs. The Soviets were working on what would become the KH-20, fitted to the Tupolev Tu-95 Bear. Britain, by contrast, had a small handful of guided weapons firms, of which only Vickers, English Electric, and Avro had any genuine experience of large airframes capable of supersonic flight. The shortlist for the contract was therefore short by necessity rather than design. There was also the question of what the weapon was actually for. Bomber Command's planners at High Wycombe, working under Air Marshal Sir George Mills, had concluded that the targets which most warranted attack, the Soviet Air Defense Command posts and the long-range radar stations of the Tallinn Line, were precisely those most heavily defended. Any aircraft attempting to deliver a gravity bomb to such a target would be lost. The standoff concept allowed the Vulcan and Victor crews to release their weapon from outside the radar engagement envelope and turn for home. Whether such a weapon could actually be built within the timescale and budget remained, in the spring of 1955, a question nobody in Whitehall was willing to answer in writing. The contract for what would become Blue Steel was placed with Avro and Company on the 7th of March 1956, though the formal instrument of agreement was not signed in Manchester until the following month. The decision to favour Avro over the competing submissions from Vickers Armstrong and from Hawker Siddeley's Coventry team rested on several considerations, not all of which were strictly technical. Avro's chief designer, Roy Chadwick, had died in the Tudor II crash at Woodford in 1947, but the design office he had built remained the strongest in British heavy aviation. The Vulcan was already flying. The team understood the carrier aircraft intimately, and Sir William Farren, who had taken over technical direction of the firm, was a former director of the Royal Aircraft Establishment, with the political reach the project would clearly require. The work was given to a separate division within Avro, the Weapons Research Division, established under the direction of Wilfred James Gerald Carr at the Woodford Aerodrome in Cheshire. Carr had previously worked on the Blue Bore television-guided bomb, cancelled in 1954, and brought with him a cadre of engineers already familiar with the peculiar problems of guided weapons. The decision to locate the design office at Woodford rather than at Chadderton, where most Avro production occurred, reflected the security classification of the project. The site was perimeter fenced, the drawing office windows fitted with frosted glass, and the staff vetted by the security service to a standard then known as positive vetting, the same level applied to staff at the Atomic Weapons Research Establishment. Operational Requirement 1132, as written into the contract, ran to considerable length. The weapon was to weigh no more than 17,000 pounds at launch. It was to be carried semi-recessed in the bomb bay of both the Vulcan Mark II and the Victor Mark II, with the Valiant excluded on grounds of structural inadequacy. The cruise speed was set at Mach 2.3, the launch altitude at 50,000 feet, and the range at not less than 100 nautical miles. The guidance system was to be entirely self-contained, with no reliance on radio updates from the carrier aircraft after release, since such updates would betray the bomber's position to Soviet direction-finding equipment. The warhead bay was specified to accept the green granite small device then under development at Aldermaston, later superseded by the Red Snow physics package. The technical demands embedded in those specifications drove the cost upward from the first month of detailed design. The semi-recessed carriage requirement meant that the weapon's shape could not be optimized purely for aerodynamic performance. The fuselage had to fit the bomb bay contours of two different aircraft, each with its own structural particulars. The Vulcan's bay was wider but shallower than the Victor's, and the weapon's external profile had to accommodate both without compromise. The result, as the Bristol-trained aerodynamicist Henry Davies noted in an internal memorandum dated April 1956, was a missile that would require considerably more powerful propulsion than a cleaner shape would have demanded, and consequently more fuel, and consequently a heavier airframe to contain that fuel. The Air Ministry's project officer, Group Captain John Rowlands, who had served as armament officer on the Hiroshima mission as the Royal Air Force's observer, visited Woodford on the 11th of June 1956. His report, held at Kew under reference A.V.I.A. 6-5/7412, recorded the design team's confidence that the airframe could be flown within 30 months. The propulsion system, he noted with what would prove to be considerable understatement, presented certain difficulties yet to be fully appreciated. The airframe that emerged from the Woodford Drawing Office during 1956 and 1957 was, by any reasonable measure, the most demanding structure ever built in Britain for serial production. The skin temperature at the design cruise of Mach 2.3, calculated using the Eckert reference enthalpy method, then standard at the Royal Aircraft Establishment, would reach 270 degrees Celsius on the leading edges and around 220 degrees on the upper fuselage. At those temperatures, aluminium alloy of the sort used in the Vulcan itself began to lose its mechanical properties within minutes. The decision was taken, and confirmed by the Avro Stress Office in a paper dated October 1956 that the entire primary structure would be fabricated from stainless steel with high temperature areas in Inconel. The choice was not made lightly. Stainless steel, in the grade selected, was roughly 3 times the density of aluminium alloy. To compensate for the weight penalty, the skin had to be made as thin as the manufacturing process permitted, which in 1956 meant a minimum gauge of 22 thousandths of an inch over much of the fuselage. Welding such sheet to the substantial internal structure of bulkheads, longerons, and fuel tank walls required techniques that no British factory then possessed at production scale. The Avro shop floor at Woodford spent the better part of 2 years developing the procedures, with much of the early work conducted under argon-shielded inert gas welding equipment imported from the United States. The cost of the welding program alone, recorded in Ministry of Supply progress reports for 1957, exceeded the original development estimate for the entire missile body. The Inconel sections, used for the nose cone, the wing leading edges, and the fin tip, presented their own peculiarities. The nickel chromium alloy was at that time produced in Britain only in small quantities by the Henry Wiggin Works at Hereford, originally for the Bristol Olympus turbine blades. Each sheet had to be hand-formed over heated dies, with the rejection rate during the first year of fabrication running at slightly over 40%. The Public Accounts Committee, in a session held in March 1961, was told that the per-pound cost of finished Inconel components in blue steel exceeded that of finished silver at the contemporary London Metal Exchange price. The figure was not disputed by the ministry witness. The aerodynamic shape itself, with its slender delta wings of 4% thickness to chord ratio and its all-moving canard foreplanes, demanded tolerances that no British aviation factory had previously been asked to maintain on a production article. The wings, manufactured at the Avro plant at Bracebridge Heath near Lincoln, were assembled on jigs accurate to 2 thousandths of an inch over their full 8-foot span. By comparison, the Hawker Hunter wing was built to tolerances of around 15 thousandths over a comparable dimension. The man-hours required to produce a single blue steel airframe, when the figures were eventually compiled by the Ministry of Aviation in 1962, came to roughly 35,000. The Hunter, a complete aircraft including engine installation, required approximately 14,000. There was, additionally, the matter of kinetic heating tests. Specimens of the actual airframe construction were subjected to thermal cycling at the Royal Aircraft Establishment Bedford from 1958 onwards, in a facility specially commissioned for the purpose. The rig consumed quantities of electricity that required Bedford to negotiate a separate supply arrangement with the Central Electricity Generating Board. The Treasury's costing memoranda, found in T 225 files at Q, show this single test installation absorbing £180,000 before it produced its first usable result. The propulsion problem was placed in the hands of Armstrong Siddeley Motors at Coventry, a firm with a respectable record in conventional aero engine work, but no significant experience of liquid propellant rocketry beyond the small Snarler motor flown experimentally in a Hawker P. 1172 in 1950. The contract for what would become the Stentor rocket motor was signed in August 1956. With a development cost estimate of £1.25 million and a completion date set for the spring of 1960. Both figures, in the manner of British aerospace projects of that decade, would prove to be works of imagination. The fuel system selected was high-test hydrogen peroxide as oxidizer and kerosene as fuel, with the peroxide decomposed over a silver-plated catalyst pack to generate the steam that drove the turbopumps. The choice of hydrogen peroxide at 85% concentration rather than the 90% then under trial at Westcott for the Black Knight rocket was made on grounds of relative stability in service storage. The decision, taken at a meeting at St Giles Court in September 1956 between the Director of Guided Weapons and the Armstrong Siddeley team, led by Dr. Lionel Haworth, accepted a 15% reduction in specific impulse in exchange for what was believed to be safer handling at dispersal airfields. The wisdom of that trade-off would be debated within Bomber Command for the remainder of the weapon's service life. The Stentor was, peculiarly, a twin-chamber motor. A large chamber of approximately 24,000 pounds of thrust handled the acceleration phase from launch to cruise altitude and speed. A smaller cruise chamber of around 4,000 pounds of thrust then sustained the weapon through the long high-altitude run to the target. The two chambers shared turbopumps and propellant feed lines, but operated independently in terms of combustion. The arrangement was unique in Western rocketry of the period and reflected the peculiar flight profile demanded by Operational Requirement 1132, which called for a steep climb to 58,000 feet, followed by an extended cruise at Mach 2.3. The development troubles began almost at once. The catalyst packs, manufactured by Bristol Aerojet at Banwell in Somerset, suffered from poisoning when trace contaminants in the peroxide came into contact with the silver mesh. Combustion instability in the large chamber destroyed 3 test articles at the Armstrong Siddeley test stand at Ansty between November 1957 and April 1958, with one explosion sufficiently violent that windows were broken in the village of Shilton, 3 miles distant. The injector design had to be revised 4 times before stable combustion was achieved across the required throttle range. Each revision required new tooling, new test articles, and new approval from the Ministry of Supply's Propulsion Directorate at Shell Mech's house. The handling problem at squadron level, foreshadowed at the original meeting in 1956, proved every bit as awkward as the skeptics had feared. High-test peroxide reacts violently with virtually all organic materials, including the cotton overalls then issued to Royal Air Force armourers. The fueling procedure adopted in service required the ground crew to wear PVC protective suits with separate breathing apparatus, and the dispersal pans at Scampton and Finningley were fitted with deluge water systems capable of flooding the entire pan within 30 seconds. The cost of these ground installations, added to the per-missile fuel handling equipment, raised the operational overhead of Blue Steel to figures that the Treasury's Permanent Secretary, Sir Frank Lee, described in a minute of January 1962 as frankly disquieting. The navigation problem set down in Operational Requirement 1132 was, in some respects, the most ambitious element of the entire specification. The weapon, once released from the carrier aircraft at 50,000 feet, was required to fly autonomously for up to 100 nautical miles, climb, cruise, descend, and arrive over its target with an accuracy of less than 1 nautical mile. No external radio updates, no terrain following, no celestial fixes. The missile had to know where it was at every moment, and to know it from the inertial forces acting upon its own instruments. In 1956, the year the contract was placed, no British weapon had ever achieved such a thing. The Americans had begun work on inertial guidance for the Navajo and Snark programs, but the technology remained in its infancy on both sides of the Atlantic. The contract for the guidance system was placed with Elliott Brothers of Borehamwood, a firm that had distinguished itself during the war through gunnery prediction equipment, and had since moved into early computing with the Elliott 405. The work was led by John Bumstead, the company's chief engineer for inertial systems, and conducted at the Elliott Aviation Division at Rochester in Kent, in a building cleared of all other projects for security reasons. The system that emerged consisted of a 3-axis stabilized platform mounted on gimbals, carrying 2 rate-integrating gyroscopes and 3 accelerometers, with an analog arithmetic unit interpreting the signals and feeding course corrections to the autopilot. The gyroscopes were the heart of the problem. Each unit had to maintain its reference axis to within seconds of arc over a flight of 15 minutes in an environment that included the launch acceleration of nearly 5 gravities, the airframe heating of 270 degrees Celsius, and the vibration spectrum of a rocket motor running at full thrust. The bearings of the gyro wheels were manufactured at Borehamwood to tolerances that the trade journals of the period described, without exaggeration, as the finest precision engineering then practiced in Britain. Each gyroscope took approximately 3 months to build, test, and calibrate, and the rejection rate during the first 2 years of production stood at slightly over 60%. A single, completed gyroscope, by 1960, cost the Ministry of Aviation roughly £2,400. Each missile required 2 such gyroscopes, plus a spare retained at squadron level. The arithmetic unit itself was an analog computer of considerable sophistication, using direct-coupled valve circuits to perform the multiplications and integrations required to convert accelerometer outputs into position estimates. The choice of valves, rather than the new silicon transistors then appearing in laboratory use, was made on grounds of radiation hardness, since the warhead bay would, in the event of a successful Soviet nuclear pre-detonation, expose the electronics to gamma flux. Transistors of 1956 manufacture were known to fail catastrophically under such conditions. The decision added weight, power consumption, and reliability problems, but it was thought defensible at the time. The cost of a single complete guidance set, when the figures were eventually disclosed to the Select Committee on Estimates in 1963, came to slightly over £5,400 at 1962 prices. A semi-detached house in Welwyn Garden City was advertised in the Times of June that year at £3,250. Each blue steel carried the price of 1.5 such houses in its nose section alone, and the Royal Air Force was ordered to procure 57 operational rounds, plus spares for trials and training. The warhead bay of blue steel was designed to accept a physics package of approximately £1,200 in mass and 48 inches in length. Dimensions that place considerable constraint on the weapon designers at the Atomic Weapons Research Establishment at Aldermaston. The original specification, agreed in 1955, had assumed the green granite small device then under early development, which was to be a British implementation of the staged thermonuclear principles deduced from the analysis of fallout debris collected after the American Castle Bravo test of March 1954. Green granite small was, in the event, never carried operationally. The yield achieved during the Grapple 1 trials at Christmas Island in May 1957 fell substantially short of the megaton figure that had been advertised to the Cabinet, and the warhead designers under Sir William Penny returned to Aldermaston with a problem. The solution that emerged over the following 2 years was the device designated Red Snow, which was in essence an anglicized version of the American Mach 28 warhead. The information transfer was made possible by the 1958 amendment to the United States Atomic Energy Act, secured by Harold Macmillan during his Washington visit of October 1957 in the aftermath of the Sputnik shock. The amendment permitted exchange of weapons design data between the two governments for the first time since the McMahon Act of 1946 had severed the wartime collaboration. Red Snow was assembled at Burghfield, the production site adjacent to Aldermaston, from components manufactured at Cardiff, Lanarkshire, and at the rolling mills at Cappenhurst. The yield was approximately 1.1 megatons, contained within a physics package that fitted, with several inches to spare, into the warhead bay specified for blue steel. The security overheads attaching to Red Snow were of a different order to those that had governed the original blue Danube freefall weapon. Every individual involved in design, production, transport, or maintenance of the device was subject to positive vetting renewed every 5 years, with continuous surveillance during periods of foreign travel. The convoy arrangements for moving warheads between Burghfield and the Bomber Command dispersal stations involved Royal Air Force Police, Ministry of Defence Police, and on certain occasions a covert escort drawn from the Special Air Service Regiment, then quietly re-established after its post-war disbandment. The annual cost of these arrangements, when finally aggregated by the Treasury's Defence Costing Branch in 1964, came to approximately £1,800,000 against the Blue Steel programme alone, a figure that was never published and which appeared in Cabinet papers only as Class 2 operational support. The integration of the warhead into the missile presented its own difficulties. The fusing system, designed at Aldermaston in collaboration with Avro's armament team, had to function reliably after the thermal stresses of supersonic cruise, the launch acceleration, and the violent maneuvering of the terminal dive onto target. The barometric fuse unit, calibrated to detonate at a preset altitude above the target, was tested at the Foulness Range in Essex during 1959 and 1960, with telemetry recorded by the Royal Aircraft Establishment Instrumentation Team based at Orfordness. The rejection rate during initial fuse testing exceeded 30%, and the unit cost of a complete fusing assembly, when the figures were finally compiled, came to nearly £1,100. Adding the Red Snow physics package itself at approximately £420,000 in production cost, the warhead alone accounted for the price of 2 complete Hawker Hunter fighters before a single component of the airframe or guidance system had been touched. The introduction of blue steel to operational service required the modification of every Vulcan Mach II and Victor. Mach II intended to carry the weapon, and the alteration was considerably more extensive than the Air Ministry had originally anticipated. The bomb bay doors had to be removed entirely and replaced with cutouts to accommodate the semi-recessed carriage. The hydraulic and electrical connections between aircraft and missile required new looms, new control panels at the navigator's station, and new test equipment for pre-flight checks. The Vulcan. Mark II airframes destined for the carrier role were modified at the Avro Woodford line, while the Victor conversions were carried out by Handley Page at Radlett. The unit cost of conversion, recorded in Ministry of Aviation files at Q under AVIA 18/3492, came to approximately £110,000 per aircraft against a new-build Vulcan price of just under £1 million. The operational stations selected for blue steel were Royal Air Force Scampton in Lincolnshire and Royal Air Force Finningley in the West Riding, with number 83 Squadron at Scampton becoming the first unit to receive the weapon in February 1963. The dispersal arrangements at both stations required substantial civil engineering work. Each operational readiness platform had to be fitted with the deluge water system already mentioned, with peroxide-resistant drainage running to settling tanks at the airfield boundary. The dispersal pans at Scampton were laid in concrete to a thickness of 18 inches, reinforced to withstand the blast overpressure of a fully fueled missile detonating accidentally during the loading sequence. The cost of the ground installations at the two stations, plus the 4 Class 1 dispersal airfields at Coningsby, Cottesmore, Wittering and Waddington exceeded £8 million at 1962 prices. The trials programme that preceded squadron service was conducted, by necessity, outside the United Kingdom. The British Isles offered no range of sufficient length to accommodate the full flight profile of a Mach 2.3 weapon, and the political climate made overflight of foreign territory impossible. The decision was taken in 1959 to use the Woomera test range in South Australia, operated jointly by the Royal Australian Air Force and the British Ministry of Supply, where the wide open spaces of the Stuart Highway corridor permitted unrestricted instrumented flight. The detachment, designated the Weapons Research Establishment Blue Steel Trials Unit, was based at Edinburgh Field outside Adelaide, with the launches conducted from Lake Hart and the impacts recorded at Talgarno in Western Australia, some 1,200 miles distant. The trials ran from May 1960 until October 1963. Of the 48 rounds fired, the success rate, defined as a flight in which all major systems functioned within specification, stood at 57%. The Public Accounts Committee, examining the programme in March 1963, was given figures that produced something close to consternation in the committee room at Westminster. The total development cost, originally estimated at £4 million, had risen to £60 million. The unit production cost of an operational round, including warhead, guidance, and all spares, had reached approximately £1,100,000 at 1962 prices. The Lightning Mark III interceptor, the frontline fighter then entering service with Fighter Command, cost approximately £370,000. The English Electric Canberra, still in service at Royal Air Force Whiten, stood at around £120,000. Blue Steel had become, in the literal arithmetic of the Ministry's accounts, the most expensive single munition ever procured by the British state in peacetime, and the committee said so in plain terms. The cancellation of Blue Steel as a development programme came in stages, beginning with the abandonment of the proposed Mach II variant in December 1960. The Mach II would have offered a range of approximately 600 nautical miles, achieved through a ramjet sustainer fed by kerosene from larger tanks, and was intended to keep the V-force credible into the 1970s. The development cost projected by Avro for the Mach II, presented to the Defence Research Policy Committee in October 1960, came to a further £40 million. The Treasury declined. The decision was taken to procure the American Skybolt air-launched ballistic missile instead, on terms negotiated by Harold Watkinson as Minister of Defence at the Camp David meetings of March 1960. Skybolt itself was cancelled by Robert McNamara on the 7th of November 1962, a decision communicated to London with what the British side regarded as inadequate notice. The crisis that followed culminated in the Nassau Conference of December that year, where Macmillan secured from President Kennedy the Polaris submarine-launched ballistic missile in compensation. The strategic deterrent was thus transferred from the Royal Air Force to the Royal Navy, and the operational rationale for Blue Steel collapsed with it. The weapon nonetheless entered service in February 1963, as already noted, and was retained as an interim deterrent until the first Resolution-class submarines became operational in 1968. The final withdrawal of Blue Steel from the Royal Air Force inventory was completed on the 31st of December 1970, when No. 6 117 Squadron at Scampton stood down from its quick reaction alert commitment. The total programme cost, when finally aggregated by the Ministry of Defence accountants in 1971 for the closing summary held at Kew under AIR 20/12117, came to approximately £140 million at the prices then current. 57 operational rounds had been built. 25 had been expended in trials, training, and reliability firings at Aberporth and Woomera. 32 remained at the point of withdrawal, of which the warheads were returned to Burghfield for dismantling, and the airframes were scrapped at Henlow and at Number 16 Maintenance Unit at Stafford. What is one to make of the Blue Steel programme as an episode in British strategic history? The Cabinet Office Joint Intelligence Committee, in a retrospective assessment circulated in 1972 and now available at Kew under reference CAB 186/10, judged that the weapon had served its purpose adequately in the period 1963 to 1968, in the sense that it had presented Soviet air defense planners with a problem they had not entirely solved at the point of its withdrawal. The Soviet S-200 surface-to-air missile, deployed in operational numbers from 1967, would in time have made Blue Steel's launch profile considerably more dangerous, but the weapon was gone before that confrontation arrived. The deeper lesson lay elsewhere. Blue Steel was the last major guided weapon designed and built entirely within British industry, drawing on British metallurgy, British rocketry, British inertial guidance, and British nuclear physics, without significant foreign technology transfer except for the warhead itself. The programme demonstrated that such an undertaking was possible, but it also demonstrated the cost. The ambition of being a fully sovereign nuclear power, exercised through indigenous means, exceeded what the British economy of the 1950s and 60s could comfortably bear. Polaris, and subsequently Trident, were procured from the Americans precisely because the Blue Steel ledger had spoken plainly. The missile had cost more than a fighter jet because in the final reckoning it had cost rather more than that.